It's the moment we've all been waiting for. The Euclid Consortium have finally released a new set of amazing images from the Euclid telescope, and today we can just enjoy the amazing power that this telescope has to offer. I'm Seti. I'm a PhD student studying galactic dynamics. I also make a lot of space-based content covering various areas of astrophysics such as black holes, dark matter, deep space like today, and other things like planetary science and the solar system. If you're interested in any of those, I highly recommend you subscribe. Let's just have a quick refresher on what Euclid is. Euclid is a space-based telescope designed to observe in the optical and the near-infrared. It's a bit similar to JWST in terms of its wavelength range, however it's just slightly shifted towards the bluer side. This wide range of light allows it to calculate redshifts for a vast amount of galaxies, primarily in deep space. Its main strengths are, in my opinion, its spectacular resolution and its wide field of view, which will enable scientists to see more galaxies and get a better view of large-scale structure in the deep universe. Alongside improving our understanding of the cosmic web, Euclid will hopefully shed light on other topics such as the Hubble constant, which I am personally very invested in, dark matter, dark energy hopefully as well, and gravitational lensing. I think by far the most popular images are of Euclid's deep field images. We've got 3 so far, so we've got Deep Field North, South and Fornax, which is in the Fornax constellation. If you go onto the actual images, you can zoom in a lot and pick out a lot of detail. It's quite mesmerizing. Within just this image of the Fornax constellation alone, there are up to 5 million galaxies that Euclid has spotted, and this is just one observation. In the upcoming years, Euclid will actually make 52 observations of this specific patch of the sky, so there will be way more information in the years to come. This image has been zoomed in 70 times into one of Euclid's deep field images, so you can really see that there is a huge amount of detail in each of these images. Personally, I think this would be a perfect screensaver for your computer because it is just so full of detail. It showcases many really unique structures like galaxy clusters, which host galaxies of varying types of and distances, but it also features a lot of gravitational lensing, which is kind of amazing to me because like 10 years ago, little me would have never thought that we'd see this many lensed galaxies in the universe, and yet every time we take a deep field picture of them we just see like dozens pop up. Speaking of galaxies, the next image or set of images that I want to show you is a collage of different spiral galaxies picked out from the deep field images. You can see quite a wide range of different morphological characteristics within these galaxies. Some of them look a little bit more diffuse and like sparse and light and airy, whereas some of them actually have quite strong spirals. Some of them also feature bars, and a couple of them as well will include tidal tails, and that usually indicates that there's an interaction with another galaxy or it's merging with another one. Another thing that I was able to just very slightly spot, but the average person probably wouldn't be able to pick up on, is that some of the galaxies, specifically the ones that are viewed edge on, such as the ones on the leftmost column, tend to be a little bit more brighter overall than ones that appear face on. Now, there are other factors at play, for example, the distance to the galaxy, so a more distant galaxy will of course be a lot fainter. However, in general, we do tend to notice this bias in astronomy and observational astronomy, and this is called an orientation bias. It's one of the many biases that we come across when it comes to cosmological surveys and deep field astronomy, but it's kind of interesting to sort of see it here in this collage. You might also notice that some of the galaxies that have tidal tails, or you can see 2 galactic cores merging together, also tend to be a little bit brighter as well. And this is because when a galaxy is interacting, it tends to get a big sort of burst of star formation, and that can also intrinsically brighten up the galaxy. The final image that I want to talk about that was released this March is arguably my favourite, and that is the Cat's Eye Nebula. The Cat's Eye Nebula is a very popular planetary nebula among amateur astronomers, well, amateur astronomers with powerful enough telescopes. And it was really key in us being able to figure out that planetary nebulas were different compared to regular nebulas and supernovae remnants. You might be looking at this image and think, hold on, this does not look anything like those Cat's Eye Nebula images that I've seen floating around the internet. Is this a different nebula? And actually the answer is no. You might not know this, but a lot of images of planetary nebula, with the Cat's Eye in particular, are made using more than just visible light observations, particularly X-ray. Within this nebula is a dying Wolf-Rayet star, and these are quite massive and very violent stars. So as they age and eventually, like in this case, die, they release large amounts of energy energy into the surrounding gas, migrating it all outward into its distinctive shells, but also heating it and ionizing it. This means it's a remarkably good target object to observe across the entirety of the electromagnetic spectrum. Another example would actually be the Crab Nebula, so Messier 1, which we have amazing images across the entirety of the light spectrum. But in the Cat's Eye Nebula, this is especially a good case for high energy photons such as gamma rays and particularly X-rays. So a lot of images you see of the Cat's Eye Nebula have multiple wavelength bands stacked on top of each other, which then get highly contrasted and colorized because we can't really see X-rays or UV or gamma rays, so we need to be able to colorize it in a way that we can interpret as humans. Euclid's image, however, is a lot more selective due to its narrower observing capabilities. So this image only includes the optical and the near infrared that Euclid has observed, and you can see the nebula is not as colourful and active looking as you'd see with other images of it, but it's kind of a bit oxymoronic in a way that such a very violent and active sight actually comes across to humans as a very peaceful and serene area. These aren't actually the first set of images that Euclid have released. Since its launch in 2023, it has been releasing a couple images here and there as testers, and I'd like to talk about the Horsehead Nebula one because it is one of my favourite images by far, and even though it's technically not one of the newer images, I still think it's worthy of being talked about. So moving much closer to us compared to the deep field images, the Horsehead Nebula is actually a perfect example of a dark nebula. This patch of the sky is particularly interesting because we expect it to be a site of star formation, particularly low mass stars like brown dwarfs. Behind the Horsehead is a lot of hydrogen gas, which is being ionized by the brightest star in Sigma Orionis. With Euclid, this hydrogen gas appears as the purple, mythical looking background behind the Horsehead, which I think is just so amazing. But one thing you might not realise is that you can sort of make out these very faint sort of vertical streaks in the image, and these are actually created by the star's magnetic field. Now, the actual head of the horse contains a lot of thick and heavy dust and cold molecular hydrogen, which is why it blocks a lot of the light from coming through and makes the shape of the horse's head. It looks a little bit more translucent in this image compared to a lot of other images by other telescopes, and I'm thinking that's because of one of two reasons. One, in the post-editing, they didn't increase the contrast as much as other telescope organisations and consortiums did, which is completely fine. And then the second reason is that we're also looking at it through the near-infrared. And the near-infrared, and I guess infrared as well, tends to pierce through dust slightly better than very blue wavelengths like UV or blue light and whatnot. So that might also be contributing to it, although I don't know for sure. That wraps up all the images I wanted to talk about today. I hope you enjoyed them as much as I did. I'm going to leave links to them in the description so you can download very high resolution versions of these images and have a look at them yourself. I'm going to also leave a link to an ESA webpage that has a zoomable version of Euclid's deep field images that you can spend hours playing around with, in my opinion. It's quite fun to have a look at. So I highly recommend you go and check that out. If you like the video, please remember to like, and if you like this kind of content, I highly recommend you subscribe, and I shall see you very soon for the next video.